Hello everybody. So in this video we're going to talk about Thevenin equivalent. Okay, this is something we discussed previously in the lecture, but I'm going to give a brief summary again. Okay, so what does Thevenin theorem say? So consider there is a circuit which is made of voltage sources and current sources and resistors, and these sources can be either dependent or independent, and they could be connected any way. Okay, so there's a complicated mess of circuits with all these components inside this, and there are two wires coming out of the box, let's say. Okay, so now as long as the circuit contains only these sources here, as long as the circuit contains only these components, Thevenin theorem says that you can replace that entire circuit with a circuit which looks like this. Okay, again, as we discussed, this is a big statement we made here, right? And this is true only for linear circuits. Okay, and in this case, these are what we're dealing with are linear circuits, because when you write the equations to solve the circuit, all the equations you write are linear equations. Okay, and that is why these are linear circuits, and this is only possible for linear circuits, right? And I will I'll just stop it there, and I'm not going to go into details on how you can prove that. But for the purpose of this course, you need to know that if this is a linear circuit, you can replace the entire circuit by something which looks like that. Okay, so now what do I mean by replace? Right, let me get rid of these guys first. Okay, all right, so what do I mean by replace? Right, replace means that if there's any circuit, where any bigger circuit where I have this, I can replace the entire thing with something which looks like this, and nothing will change in the remaining part of the circuit. That means if there was something else here, then if I replace this part of the circuit with with this circuit, nothing in here will change. Okay, so that's what that means. So that's what replacing this with this means. Okay, so all right. Okay, so get rid of more than what I wanted. Okay, so all right, so now that we can assume that that's what we can do. So the next question is, how do you actually measure VTH and RTH, right? And VTH because it's called Thevenin voltage, RTH because it's called the Thevenin resistance. Okay, so the question is, how do you measure this? Let's say if you're in a lab and you're given this circuit, right? And I ask you to replace that with this circuit by selecting the proper values for VTH and RTH, right? And you have all the equipment in the lab and ask you, okay, how do you take measurements and determine the values of VTH and RTH, right? So now remember I said these two circuits behave exactly the same way, right? So that means if I take a voltmeter, plus minus, let's say voltmeter, and I connect a plus here, minus here, right? I will measure, because ideal voltmeter is supposed to have infinite resistance. That means it's acting like an open circuit, right? So that means there is no current going in here. If there's no current through RTH, there is no voltage drop across RTH, and this VTH, this voltmeter, will measure VTH. Okay, so now I'm measuring the voltage across these two terminals, or between these two wires, without connecting anything here, right? That's why this is called the open circuit voltage, right? So that's what I have here. VTH is the open circuit voltage. What that means is, in the lab, you take the voltmeter and connect it here. Okay, and whatever you measure is the value of VTH, right? Okay, so now we know how to measure VTH. The next question is, how do you measure RTH, right? So again, we'll use the fact that these two circuits behave exactly the same way, right? So if these two circuits behave exactly the same way, if I short it like this and measure ISC, because these two circuits behave exactly the same way, if I short it here and measure ISC, I should measure exactly the same current. Okay, so all right, on the right hand side, if I measure ISC, we know that ISC should be equal to VTH, divided by RTH, right? So this implies RTH will be equal to VTH divided by ISC, right? So again, if you're in the lab and I give you this circuit and there are only two wires coming out, and I ask you to measure RTH, then all you need to do is short it, measure ISC, right, and use this formula here to measure RTH, and that's the second point here. ISC is a short circuit current, and the Thevenin resistance is VTH divided by ISC. Okay, so let's do an example now. So this is example 4.14 in your textbook. So this is the circuit given on the left hand side, and our goal is to calculate an equivalent circuit which looks like which looks like on the right hand side. So basically we want to replace the left hand circuit with the right hand circuit. Okay, and in other words, we want to compute the Thevenin equivalent for the left hand circuit. All right, so the first step is calculate the open circuit voltage, right? So keep this open, don't connect anything here, and measure the voltage here, and that should be equal to VTH, right? Okay, so remember, if you don't connect anything here and this is open, that means the current here is zero, right? So that means this VTH is equal to this voltage over here. It will be equal to voltage over here. Okay, like that, right? So this is equal to VTH because there is no voltage drop across the 4 ohm resistor if you don't connect anything here at the output side. Okay, so then all I need to do is calculate the voltage across the 20 ohm resistor in order to calculate VTH. So okay, now if I want to, then I can use all the circuit analysis techniques I used to do this, right? If you're in the lab, you won't do any calculations, you just take a voltmeter and measure VTH directly, right? But now our goal is to actually do calculations and do this by hand manually without the voltmeter. So but we do have an advantage of looking inside the circuit, so we can do all sorts of calculations. All right, so all right. So if I want to measure VTH, so I can, let's see, how many essential nodes do I have here? I have one essential node here and another essential node here. And that's it. So two essential nodes, right? So I probably go, and then if I want to, so if I only have two essential nodes, that means I need only one KCL equation if I use the node voltage method. But if I use the mesh current method, I need two meshes here, right? So because there are two loops, one loop here, one loop here. So I'll just go with the node voltage method because I will only need one equation, right? So let's do that. So node voltage method. Let me see if I can get rid of these guys. Okay. All right. So if I want to do the node voltage method, then I will consider this to be my ground, right? So that means this is 0 volts. If this is 0, according to the definition of the 25 volts voltage source, this point here should be 25 volts. Okay, and this is VTH, which I want to measure or calculate in this case. And that's it, right? So let's say this be I1, this is I2, and this is I3. So KCL says I1 plus I2 plus I3 equal to 0, right? Now all I need to do is convert these currents in terms of voltages, right? So I1 is the current from left to right on the 5 ohm resistor, through the 5 ohm resistor. So that means that will be equal to the voltage drop. That will be equal to the voltage drop from left to right. So that will be 25 minus VTH divided by 5 plus I2 will be the voltage drop from bottom to top. So that will be 0 minus VTH divided by 20 plus I3 is equal to 3 amps. And this would be equal to 0. Okay. All right. So all I need to do is solve this. So I'm gonna pause the video and solve this. So here is my solution. So I just brought VTH terms to one side and factored VTH out over here. And I just solved it, and then I got VTH is 32 volts. Okay, so now I know what the Thevenin voltage is. Okay, so then we go to step 2, where you find the short circuit current, right? So I replicate the figure here. So what I need to do now is, okay, I can keep this color, short circuit this, find the short circuit current. Okay, so now this is another circuit. I just need to analyze this circuit to figure out what ISC is, right? So again, I can either do mesh current method, in which case I'll have to do 3 loops, right? Or I can do node voltage method, in which case I have one essential node here, another essential node here, and that's it, right? So that means I will not probably, I will need only one equation to solve this or analyze this circuit using node voltage method. So I'm going to do that. Okay, so all right, I'm going to consider this as ground. So the voltage here is 0, the voltage here is 25. Let's call this V, and I want to do a KCL equation at that node. Okay, all right, so let's say that is I1, that is I2, I3, and I4. Okay, so KCL tells me I1 plus I2 plus I3 plus I4 is equal to 0. Okay, now I need to convert this into voltages. I1 is the current through 5 ohms from left to right. So the voltage drop from left to right is 25 minus V divided by 5 plus I2 bottom to top 0 minus V divided by 20 plus I3 is 3 amps plus I4 is minus ISC. So this should be ISC. So I4 is minus ISC is equal to 0. Okay. Yep. Let's see. Well, I can actually write ISC in terms of V here, so that I don't need another equation. I don't need another variable. So I4 is the current through the 4 ohm resistor from left to right, right? So that means I can do plus. Then the voltage drop from left to right is 0 minus V divided by 4 equal to 0. Okay. All right. And then I just need to solve this to find V first. So let me take V to one side and factor it out. 1 over 5 plus 1 over 20 plus 1 over 4 will be equal to 25 over 5 plus 3. Okay, that's it. So this will be equal to 8. Over here, the least common multiple is 20. So I have 4 plus 1 plus 5 is equal to 8. This implies V is 20 times 8 divided by 10. Okay, so this will be equal to 16 volts. Okay, in this case, when you short circuit it, I have 16 volts over there. Then you can see ISC, the short circuit current, would be the current flowing through the 4 ohm resistor from left to right, right? So that will be V minus 0 divided by 4. So that means my ISC is equal to 16 divided by 4. That will be 4 amps. Okay, and my VTH is equal to 32 volts. This implies my R Thevenin is equal to 32 divided by 4 will be equal to 8 ohms. Okay, let's dig a little bit deeper now. Okay, again, so in the Thevenin equivalent, our goal is to transform a circuit which looks like on the left to a circuit which looks like on the right. Okay, so now when I say the circuit on the right hand side, let me break this class. This circuit behaves exactly the same as this circuit. There's actually a lot more to it than than just the characteristics at the terminals. Okay, so let's see. So in the left hand side or in the right hand side, say if I zero out all the voltage sources, I get a circuit which looks like this, RTH, right? Basically, I'm setting this voltage to be zero. That means I'm zeroing zeroing out that voltage source. Okay, and then if I look at the equivalent resistance here, that I get RTH, right? So what that means is I can also do the same thing here. Zero out, zero out all voltage sources. In fact, all sources. Zero out all sources in there, right? So, and then the resulting of that, let's say, let me pick an eraser here. Okay. All right. So let the result of zeroing off all that voltage sources make it a new circuit, and then if I measure the equivalent resistance, that should also be equal to RTH because that's what it is over here. Okay, so when I say these two circuits behave the same way, it's actually much deeper way in the deeper sense, right? So it means if I zeroed all the voltage sources on the right hand side and measured the equivalent resistance, I should get the same equivalent resistance if I do the same thing on the left hand side. See, again, this is a very profound statement I'm saying here. And this is possible only for linear circuits, and it is a result of something we will discuss later called superposition principle for linear systems. But again, we are not going to go into the proof of this. But for now, I think this is important to know because this will be very helpful in some situations. And I'm going to use the same example we solved about to show you how helpful this is. Okay. Okay, so this is the same example we used before, previously when we solved for, um, when we're trying to find the equivalent in Thevenin equivalent. Okay, so here we short circuited, found out the short circuit current and used that to calculate RTH, right? So now let's use this new method where we zero out all the voltage sources and find the equivalent resistance to calculate RTH, right? So what we're going to do is in this circuit, zero out all the sources, okay? So let me zoom out a little bit, okay. So if I make the 20 voltage source zero, I should short it. And then I get a 5 ohm resistor there, 20 ohm resistor there. Okay, and notice that zeroing out a current source means opening it, right? So let's say if I open this like that, if I open this like that, then the current here is 0, right? So that means I'm zeroing out that current source, and this is 4 ohms. And then I'm looking at equivalent resistance in here, right? That should be equal to RTH, right? So again, so this is basically, if you simplify the circuit a little bit, this is 5 parallel with 20, 5 ohms in parallel with 20 ohms, right? And there's and both that is in series with 4 ohms, like that. And the equivalent resistance looking in here is RTH. So 5 parallel 20, 5 times 20 divided by 25, 5s, 4s. So this is 4 ohms. So this implies RTH should be equal to 8 ohms, which is also what we got. Let's see. I hope that's the same thing. Yep, this is also what we got over there. Okay. So so basically what I'm saying here is these two are the same methods, right? So in order to find the Thevenin equivalent, finding the Thevenin voltage is always the same. You just calculate the open circuit voltage and that's VTH, right? But in order to find RTH, you can either first calculate the short circuit current and use that to calculate RTH, or zero out all the voltage sources or zero out all the sources and find the equivalent resistance, right? Now, depending on the problem, one of these methods may be easier than the other. Obviously, in this case, the second method is easier. There could be some cases where the first method is easier. So it depends on, you can make a judgment call based on the situation to make your life easier. But both these methods are equivalent. They're doing sort of the same thing. Okay.